So yes, I'm John. I'm going to present our work on learning stance embeddings from science social graphs. And this is joint work with Akshay Gupta, Arya Ajiji, and Ahmed Elkishki. The starting point of this work is to try to understand stances online. So on any social platform, you have people who interact with each other, who debate, and by doing so, they're going to express support or opposition toward each other on various discussions and topics. So as an individual online, I could agree on with someone, I could disagree with someone else. But also, I could also agree with someone on one topic and disagree with the same person on another topic. So what we're looking at today is stances, so the position of an individual on a specific topic or towards someone else. A good way to tackle the issue of stances is to look at it from an embedding point of view. Because, so we have a science social graph, so a graph where nodes are users, interactions are support or opposition. And we also have edge attributes, which are topics. And if we're able to embed all this data into the same vector space, then we can answer many questions. Several of them we're going to try to answer today. So for example, if we're given two individuals on a given topic, can they agree or not? Then we also want to tackle the issue of, is it possible to infer the stance of an individual on a topic that I've never engaged on? And I think that's a very important question because then it has many applications, for example, in polarization mitigation, moderation efforts, and also recommendations. And eventually, we're going to look at the importance of topical information in general in such graphs. So we're going to build the model. So the literature on signed embedding graphs is basically, all the existing methods are not able to actually capture edge attributes in the learning process. So this is going to be the contribution of our work, and we're going to propose an approach that is then topic aware, flexible for edge attributes, interpretable and scalable. So this brings me to the model that we call Stance Embeddings Model, SEM. And SEM works in two steps. So in the first step, we're going to generate random walks on a signed topical graph. So first, let's forget that we have signed on the graph, and let's just generate random walks on the graph. So here I give an example of walkers that goes from C to D. So the sequence is C, A, B, F, D. And given this sequence, we can then say, if we look, for example, at node B, what is the neighborhood of node B? Well, with the given random walk we have, the neighborhood of B is C, A, F, D. And those walks are only going to span one specific topic at a time because we don't have any relationship between topics. And in fact, we're going to see later that the model is actually able to learn topic relationships in a supervised fashion. So second, we have those random walks. Now we have the neighborhood of a specific node, and we try to answer the question, what is the relationship of this specific node to its neighborhood? And the way we're going to do this is that we're going to borrow a theory from social science called strong balance theory, which has kind of three main statements. The friend of my friend is my friend, the friend of my enemy is my enemy, and the enemy of my enemy is my friend. So when we look at the sequence we have in this example, so we have C, A, B, F, D. How does B relate to its neighbors? Well, B relates negatively to C because B is a friend of A, who is the enemy of C. B relates positively to A, B relates negatively to F, and B relates positively to D because it's the enemy of one of its enemies. So what we're going to call contexts are something of the form C minus, A plus, F minus, D plus. So for doing those random walks, we're able to have training samples that are going to be composed of a topic, a source node, and the context of the source node. just what we call context. So the second step of SEM is to actually learn so a topic embedding map and a node embedding map simultaneously. And the way we're going to do this, we're going to use a modified skip graph model, which basically we tell the system, I give you a node and I give you a topic. Can you tell me, given this topic, can you tell me which other nodes are most likely to interact with this node? And if they do, what is the nature of those interactions, positive or negative, right? And by doing so, by optimizing the system so it actually predicts perfectly the context, the system is going to learn the embedding maps that we see as input. So yeah, that's it for the model. Let's go for experiments. And before this, I'm going to talk about the data we apply and we test the model on. So we have two data sets that we have built and that we open source. One of them is Twitter SG, which is the largest publicly available science social graph to date. It's 6 times larger than the largest benchmark data set. And Twitter SG, which stands for Twitter Science Graph, is an edge. Is a graph of user-user interactions. And the positive edges are going to be support that comes from likes. So I like the tweet of someone. And the oppositions come from, I guess on Twitter, you don't really have a negative feature so you don't have really a negative feature. So we have to come up with kind of some heuristic to actually retrieve negative edges. And here we do it by creating a list of basically slurs in French and English. And any tweet that is going to answer, to reply to another tweet with one of those slurs is going to be considered as a position. So eventually we have this graph and the topics, we retrieve the topics with a transformer-based topic classifier, and those going to be the edge attributes from the tweets. So eventually the graph has 750,000 nodes, 13 million edges, and 200 topics, which are all related to sports, whether it's sports teams, players, events, and you see the most frequent topics on the bottom left side. Yes, the second data set is Birdwatch SG. So you may have heard about it. Birdwatch, also called Community Notes, is a kind of a platform owned by Twitter, which enables for any participant to basically write a note on a tweet when someone thinks that the tweet may be misleading. And other participants can then upvote and downvote the note. And we're going to retrieve your position and support from those upvote and downvotes. So similar thing, we retrieve topics from the tweets. And this time we have a much smaller graph, only with 3,000 nodes, but much more topics and also a higher density. Okay, so let's go for experiments. So we have two topic-aware models, which are based on SEM. We have SEM addition. So it's a case where we take the topic embedding and the node embedding and we add them together. And the Hadamard version, which is when we do element-wise multiplication between those two embeddings. And then we have the baselines, which are all topic agnostic, as I said before. And to compare with them, we're going to introduce also a version of SEM, which is topic agnostic and simply doesn't look at the topic as input. To evaluate the model, we use something that is very common in signed embeddings methods, sign link prediction. So it's basically a binary classification problem. Given an edge, are we able to say if it's positive or negative? And to do this, we're going to create edge embeddings that are basically determined by combining the two node embeddings at stake. And we tested 5 different operations. So averaging, for example, the node embeddings, or differentiating them or whatever. So in terms of performance, the first 4 rows are the topic agnostic models. The first thing we see is that SEM mask is competitive with the 3 baselines. And when we're able to actually incorporate the topic information within the learning process, which comes with SEM addition and SEM Adamar. We see like a significant improvement in performance, which means that the model is actually able to learn better non-embeddings by conditioning topics. Well, now we can say that maybe it's unfair to compare all these models because some of them are able to use the topic information. So now what we do is that even though we're not able at not embedding learning to learn topic maps for the topic agnostic models, we're going to do it when we try to do sign link prediction. So now when we do the logistic regression, we're still going to train the logistic regression, but we're also going to include a topic map that we're going to learn at the same time. And we combine it with one of the user embeddings, and then we combine everything together as we did before. And what we see here is that even when we do this for all the topic agnostic models, they are still not able to get the same performance as SEM addition and SEM Hadamard, which means that it's actually more beneficial to have a method that is able to jointly learn both node and topic embeddings during the process. And this is what SEM is able to do. Last question we have is a cold start topic stance detection problem. So are we able to predict the stance of an individual on a topic they have never engaged on? So in the test data, we have a set of data which are composed of nodes and topics that have never been together at training time. And this is basically the most challenging data we can have, right, among the test data. And when we look at the performance of the model on this subset of the data, and when we look at all the test data, actually there is no drop in performance in between the two settings. So it means that the SEM is actually able to learn, to actually predict as well on the challenging data and the cold start problems as actually in any other issue. And I think it means that the topic, so basically SEM at learning time is able to learn topic relationship in an unsupervised fashion. And it's actually, as I said before, key for things like, for example, polarization mitigation. I've observed the opinion of someone on many topics. What can I say about other topics for this person? And just, I guess, a final point on this. We're going just to show visually that it's actually the case. SEM is able to learn topic relationships. So this is on Twitter SG. So we have a topic related to sports, and we see that we have clusters of topics related to the same sport, but also we have subclusters within some sports, which relates to, for example, players who played in specific teams, and we see that the proximity of players who play in the same team, same national team, same clubs, are going to be closer than other topics. And yes, at the end, I think in summary, the contributions are twofold. The first one is a simple, efficient, and interpretable way to learn stance representations. We also open source 2 signed graph data sets. And key takeaways, our model is able to infer stances on topics users have never engaged with, because it's able to learn topic relationship. And finally, in terms of future work, there are several still withstanding questions. Can we interpret theoretically how SEM learns, topic embeddings, topic relationship, even though we don't really, directly tell it to do it? Which topics are more important for stance prediction, and how to actually determine which are they? And are we able to also incorporate other social science theories that could get the model to get even better performance? This was my final say, and I thank you for coming and for listening.